hand rule. We put our fingers in the direction of V, we curl them toward the direction of the field, and we're going to get a force that points straight up, like this, straight up. So this is the first force, right? QV cross V. And in fact, if we write it down, there's the right angle, so the magnitude is just going to be Q times V times V. Now notice that what happens, whether it's positive charges moving up or negative charges moving down, notice that they don't have any place to go once they reach the end. So the situation that you'll have when you take a conductor and it moves the magnetic field is that positive charges accumulate here, negative charges accumulate here. That generates an electric field. So we have an electric field that's also set up here with another force associated with that. At which point does this madness stop? Well, when everything comes into equilibrium, right? So if we set the forces equal to each other, we're going to get that E is equal to V times V. So the electric field that's set up is proportional to the velocity as well as the strength of the magnetic field. If we have an electric field that is applied over a length, let's say the length of the rod is L, then we're going to have an electric potential as well. So remember from before that delta V, for a uniform electric field, the change of potential is actually going to be minus EL, absolute value. It's going to be E times L. But we know that E is V times V, so we can write an expression that looks like V times L times V. So only for this specific case, a moving conductor in a magnetic field, we have this expression for the potential difference, depends how fast it's moving, the length of the object, as well as the strength of the magnetic field inside. So far, so good. Right? Question. Now, again, this might look familiar from the pre-lecture. You say, okay, I believe kind of this mathematical manipulation. Well, what is actually happening? Well, believe it or not, it says that there is really a potential difference between this end and this end. And in fact, if it is a potential difference, it could be just like the same potential difference from a battery. In a battery, you have chemistry, chemistry, there's all this magic stuff inside, who knows how, and then you get a potential difference across the terminal, and then you hook it up to a circuit, and something can actually happen. So we could think of a chemical EMF that generates a potential difference in the battery. What we have is the equivalent of a motional EMF that's also generating a potential difference between here and here. So it can actually be used as a source of current and potential difference, just like you would a chemical battery. Right? So the electrons that are in the circuit, they don't care. It's the same thing. Right? So what would this actually look like? Well, believe it or not, if we had a situation called a slide wire. So this is what the slide wire looks like. Let's say that you have a resistor here, and you have some conducting leads here, and then you take your bar, which you had before, and you put it on your circuit. Right? So what you could imagine is that if you were actually dragging this to the right, well, let's see, I'm sorry, what would happen? If you had a current that was going through the loop, and this was in a magnetic field, what you would have is a current going through here. You would have IL cross B would give you a force to oppose that. And the way that you would move the current in the first place is that you would have to drag it to the right. So it's kind of a strange thing in which what we're doing is we're actually trying to move the bar to the right. Because we're moving the bar to the right in a magnetic field, it's generating this current which is going through the bar. And as that current goes through, it'll actually want to stop. So if we have the force that we're pulling on it, the force that is being exerted on the bar, that ends up in a constant velocity. Now if we were going to try to model this as a circuit, we would write it like this. This is R. This is the battery like this. We could say that there's an EMF that's supplying this current, and the EMF is just given by V times L times V. It should have no difference in how we're actually looking at it. Any other question? All right, so I did a poor job of explaining that. So let's try again. If I have a bar, and I pull it to the right, so I apply some force to it, so it's moving to the right, then we'll have the same situation that we have up here. It'll be like positive charges here and negative charges here, like a battery. If I hook this battery up to a circuit, then I get a current that goes from the positive to the negative, and then back through here.
current by itself is actually moving going this way. So what causes the flip is actually going here.
Oh, right. So, so we have that actually, what's happening is the potential difference is still this, you would still agree that this is a higher
No, I
potential
just
here.
got the,
Okay, all right. So, so the current goes here and then it drags. And as it turns out, I just found out that we have a way to see a force being acted upon. Eric Burton, who you might have seen here with the beer, he sets up all the labs for all the classes in all the semesters all the way. So if 105 has 20 labs and we have like 11 and 211 has like 20, he's the person who does all of the work, tearing them down and then setting them up, doing all these things too. So, okay. All right, what am I doing? I'm doing the document camera. All right. So we have here. All right. And then we actually have a magnet. So this magnet says keep away from, well, okay, it says keep away from other magnets. This is a very strong magnetic field up, and what we're going to do is we're going to run current in through here and take it out through here, but there's no way to complete the circuit. The way that we can complete the circuit is by putting another copper rod here, and then when we turn on the power supply, oh, we turn up the current. All right, let's try this again. Random demo. Okay, let's try it. It's how it moves, right? It's not enough, turn it up just a little more. All right, that's what you get when you start a demo. Say someone says, "Hey, I got this nice demo that you can show in class." I'm like, "Yeah, sure, get it. Just no problem. It'll work each time too." Okay, we'll see if I can get it, figure out what's going on, and do it next time. Or you can come at 5. You know, it's better there, or not. All right, so this is our kind of basic circuit that we have. Right? If we wanted to calculate what the current was, then it would have the EMF is given by B times L times V. Nothing any different from that. And we could even calculate the power that's in our circuit by using I squared times R. So the power would be, or V squared over R. So BLV squared over R. The fact that you have these currents that are generated when things move in a magnetic field lead to some, I think, really interesting effects. One idea is this idea of eddy currents. So for eddy currents, there's circulating currents that happen when you move a metal conductor, again, near a magnetic field. So let's see what's happening here. Is that if I take a loop of wire and then I pull it, so this is kind of the same situation that I had before. I pull it to the right, it generates a current that goes up and then around this way. But then, as I said before, because there's a current in the magnetic field, there'll be a force that opposes it. So we can imagine if we take something that has a lot of current in it, it would be the same as, when I pull it to the right in a magnetic field pointing into the board, it sets up a potential difference here. The current goes this way. I mean, this way it went this way, but because it's connected to the right, it goes this way. Cool. Now I know what to spend more time on. So you're pulling it to the right. The idea is that the magnetic force that's resulting will then want to prevent it from moving to the right. You can do this also with a bigger piece of metal like this. Notice that there are more currents because there's more path for these electrons to take, and so the retarding force will actually be greater. So in both cases, when you pull the object to the right, it leads to currents, which then induce a magnetic force. So we have, again, another demo that we can use for this. It would be this kind of copper tube. And then I take a regular ball, nothing special about this ball, and then I drop it in the tube. You see, oh, there it is, right? I just drop it in and so it is actually a special ball. It's magnetic because if I take just a regular ball, nothing special about the tube, then it comes out. What's happening is that eddy currents are useful for slowing things down, right? Like as we saw. And they're actually can be used in springs, right? So if you don't want to use a mechanical brake with pads, you can actually use this. The rails are made, can be generated, have eddy currents generating in them. They can be used to slow down a train as well. We have a way to think about, sometimes this is good, sometimes, of course, this is not so good. We have one nice demo. There's too many demos, probably. That's okay. We have this idea of an eddy current pendulum. So here we have, again, the same type of thing, a bar magnet, north and south here, and then a pendulum that we can swing and try to pass it through this magnetic field. What happens is that comes and then it slows down. Not just slows down, it's actually, well, sometimes it hits the side, and I'll turn it this way so you can see it a little bit better. So let's think about what's happening here, is that if we have it moving down here, again, we have current that's going up, but the IL cross B gives us a force going in the opposite direction. Now, sometimes this is a good thing, but sometimes we don't actually want this. If we don't want eddy currents to form, what we can do is, again, this isn't just for this, it's actually a useful physics demo, is that we've actually cut lines in it so that the size of the eddy currents that can form are very small. So if we then put this one through our pendulum, you can see actually it goes quite easily until it hits the side. If we put the two together, let's put the one that stops in front. We'll put the solid one in front. We'll make it a little bit wider, so not hit by the side. And then we'll let them go. See that one actually, well, one will swing in the other one forward too. So eddy currents, again, is this one of those things that make nice demos that actually have very practical applications. Sometimes you